Imagine a commander standing in the cockpit of a tank, surrounded by the noise of battle. The situation is chaotic, and the next move could determine the outcome of an engagement. In the past, this person relied on maps, radio calls, and their own experience to decide what to do next. Today, the goal is to speed up that decision loop, often called the Ooda loop, which stands for Observe, Orient, Decide, and Act. To do this effectively, you need intelligence that arrives instantly, without waiting for a satellite uplink or a cloud server. This is where the integration of artificial intelligence into the hardware of the battlefield becomes critical. France has recently signaled a major shift in how it approaches this challenge. By leveraging open-weight models from companies like Mistral AI, the nation is moving toward a strategy of digital sovereignty. This means reducing reliance on foreign proprietary systems that might cut off access during a conflict. But having the software is only half the battle. The real technical hurdle lies in fitting these powerful models onto the rugged, power-constrained hardware found inside military vehicles. You cannot simply ship a massive server rack into a Humvee or a main battle tank. The system must run locally, often in environments where internet connectivity is denied or unreliable. This brings us to the core of the engineering challenge. Mistral models, like many modern large language models, are designed to process vast amounts of information. They contain billions of parameters, which are essentially the mathematical weights that determine how the model interprets data. In a data center, these models run on clusters of high-end graphics processing units that consume significant power. In a vehicle, you have a much smaller budget for energy and heat. To make this work, engineers must use a technique called quantization. Think of quantization like compressing a high-resolution image into a smaller file format. The details are preserved, but the precision of the data is reduced. Instead of storing numbers as 32-bit floating points, the system might store them as 8-bit integers. This reduces the memory footprint significantly, allowing the model to fit into the limited RAM of an edge device. However, size is not the only constraint. Speed matters just as much. A model that takes 10 seconds to generate an answer is useless if a commander needs a tactical assessment in 2 seconds. This is where model pruning comes into play. You can think of a neural network like a vast forest of interconnected trees. Some of those trees are dead or redundant. They do not contribute meaningfully to the final output. Pruning involves identifying and removing those unnecessary connections. By cutting away the dead weight, the remaining network becomes leaner and faster. The model retains its core intelligence but operates with greater efficiency. This allows the system to perform complex reasoning tasks in real time, even without a connection to a central cloud server. Now consider the implications for data security. When you rely on a foreign cloud provider for your military decision-making, you are sending sensitive data across borders. In a conflict scenario, that data could be intercepted or the service could be severed. By deploying Mistral models locally, France ensures that the data stays within the vehicle and within the national perimeter. This aligns with the broader strategic goals seen in joint ventures like the one between Mistral, NVIDIA, and French state entities. The focus is on building a sovereign ecosystem where the hardware and software are designed to work together from the ground up. This co-design approach accelerates operational readiness because the software is optimized specifically for the hardware it will run on. The transition from cloud-dependent to edge-dependent AI changes the nature of warfare. It shifts the advantage from whoever has the best connection to whoever has the most robust local intelligence. In a denied environment, the side that can process information locally gains a decisive edge. They do not have to wait for permission or bandwidth. They can analyze sensor data, identify threats, and suggest courses of action instantly. This is the future of the OODA loop. The cycle of observation and action becomes so fast that it outpaces the adversary. The technology enables a level of responsiveness that was previously impossible for vehicles operating in isolated conditions. There is also a significant regulatory and ethical dimension to this shift. Open-weight models allow for greater auditability compared to closed-source alternatives. This means that the military can inspect the code and the decision logic to ensure it aligns with safety protocols and rules of engagement. While there are risks associated with open releases, the ability to verify and customize the system for specific classified environments makes it a preferred choice for defense applications. The goal is not just to have an AI, but to have an AI that is trusted, secure, and capable of operating independently when the network goes down. The infrastructure supporting this deployment involves more than just the models themselves. It requires a robust pipeline for offline inference. This means the system must be able to load the model, run it, and update it without ever touching the public internet. Updates must be pushed via secure physical media or localized networks that are isolated from external threats. This requires a complete rethinking of how software is distributed in the field. It is a logistical challenge that mirrors the physical supply chain but applies to digital intelligence. As we look at the trajectory of this technology, it becomes clear that the integration of Mistral AI into military vehicles is not just an upgrade. It is a fundamental change in how operational decision-making is executed. The combination of quantization and pruning allows for powerful intelligence to reside on the edge of the network. This ensures that the speed of the Ooda loop is no longer limited by communication latency. For the French military, this represents a strategic pivot toward autonomy and sovereignty. It is about ensuring that in the most critical moments, the decision-making power remains in their own hands, running on their own terms, and protected by their own defenses. This technical evolution marks a new era where the battlefield is not just defined by terrain and firepower, but by the intelligence embedded in the machines that traverse it. The ability to process complex data locally transforms every vehicle into a node of intelligence. It turns a collection of hardware into a distributed brain capable of surviving and adapting in the most hostile environments. The work being done on quantization and offline pipelines is the foundation of this new capability. It ensures that when the lights go out and the networks fail, the machine still knows what to do. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.